In this video, we're going to go through charged particles in uniform electric fields. So what we have in this picture is we have an electron approaching the midline between two charged plates, as we've shown here. The path that the electron would take if it were not affected by the electric field is shown. So if there were no field between here, the electron would just go straight. Let's draw electric field lines between the plates, and we're going to ignore the fringing that occurs at the edges of the plates. Electric field lines go away from positive charges and towards negative charges. This is a uniform electric field, so I'm trying to draw those lines equally spaced. Draw the trajectory of the electron between the plates. Assume that it emerges at the bottom. It's not going to go straight. What is it going to do? There are a couple ways you can think of this. When it enters this electric field, it's going to experience a force opposite the field lines. That's one way to think of it. Another way to think of it is it's going to be attracted to the positive and repelled from the negative. Its trajectory is going to look kind of like that. And from this point on, it's going to fly straight, isn't it? In other words, this right here is going to be a constant slope. Once it gets out of the field, it's going to go straight. Now we want to derive an expression for delta x, the amount the electron has veered off its straight line path. So the delta x amount would be right in here. How much it veers off by the time it emerges from between these plates. When we don't know what to do, we just need to do something. Well, this electron is going to experience a force in what we might say is the x direction, the horizontal direction, and that force is equal to the charge of the electron multiplied by the strength of the field. Now, the charge here is given as not q, but it's given as lowercase e. So we need to have all the variables that are given in this problem. Well, what else do we know? We also know that this force, which is in the x direction, I might put that, is equal to the mass of the electron multiplied by the acceleration in the x direction. And here again, the mass is given as a capital M, not a lowercase. All right, well, I don't know if that's gotten us anywhere. The electron, essentially, I don't know if you remember doing this in your studies of mechanics, but this is basically like a horizontally launched projectile, except we've flipped the axes 90 degrees. And because the force is constant, and that'll make the acceleration constant, delta x is found by using one of our, hopefully, familiar kinematics equations that looks like that. Now, the electron's velocity in the x direction is, of course, 0 in this case. So we can cross that term off. We now can figure out what ax is. Let's go ahead and simplify this as much as we can. I think we're going to have the 1/2 there. And then the acceleration in the x direction, isn't it going to be little e times big E divided by m? And then there's our t squared there. All of our variables in our answer need to be variables that are given in the problem. And that is the case for all of these except for time. Time is not given. So is there anything else in the problem? Let me scoot up here so you can see the picture again. That might give us time. And the answer is, right here, I've got this value, y, and we know what this entrance velocity is in this direction. And this entrance velocity, this v here, is going to remain constant, isn't it? Because there are no forces in that direction. And therefore, we can go this. Distance equals rate times time. Let me write an equation to that effect down here. Distance equals rate times time, which tells us that time is y divided by v, and so we can substitute that in right here. 1/2 little e, big E divided by m, and then we're going to have y squared up there and v squared down there. All of those values are given in our problem. So I think our final answer is going to be, if we want to make it look neat, we can put the 2 in the denominator. There you go. Feel free to check the units on that. I won't take the time to do that, but do a little dimensional analysis on this, and you will see that these units give you the unit meters, which is what we would expect for delta x. Lastly, why is gravity ignored when working with charges in electric fields? And that's because charges have very little mass. And because of that, gravitational forces are negligible.